Welcome to Optical Fiber Communication Laboratory Manual. Today we will discuss Practical 4. Request to like, subscribe, press bell icon, share and comment. This is the sample of certificate. Index. In earlier video lecture we have discussed optical fiber waveguide, transmission characteristic optical fibers and optical fiber and cable related example. In today's practical, we will discuss Scilab code for optical fiber connection, joint, coupler and isolator. Practical 4. That is optical fiber connection, joints, couplers and isolator. Aim to write a Scilab code for a given example of optical fiber connection related to joint, coupler and isolator. Software is Scilab with version 6.1.0. Theory. In many applications of fiber optics, it is necessary to connect fiber ends, termination, in some way such that light from one fiber can get into the other fiber without losing too much of its optical power. Examples are fiber laser and systems for optical fiber communications. There are different techniques for joining fiber ends. Permanent and stable connection with very low transmission losses can be obtained by fusion splicing. Essentially, the fiber ends are fused together with a heat treatment. Semi-permanent connection can be made with the mechanical splices, which are relatively simple alignment device holding the fiber end together. Typically, some index matching gel or an epoxy is used for reducing reflection losses. Compared with the fusion splices, mechanical splices are faster to make and can be removed after use. The initial cost is much lower, but the cost per slice is higher. The splice loss and reflection loss are of the order of 0.5 dB, that means significantly higher than for fusion splices. Fiber connectors are convenient for the connection which we need to be released more often. Common connector types are named FC, SC, LC for single mode application and ST for multimode, but there are also dozens of other types with special qualities such as duplex connection, particularly small size built-in shutter for improved laser safety, etc. In most cases, the fiber is glued into the connection with some epoxy and then fiber end is polished. The transition loss of connector are similar to those of mechanical splice, although the stability is generally lower. This is a figure of micro image of fusion splice between a photonic crystal fiber PCF left side and a conventional fiber right side. The whole pattern of the PCF can be seen. The photograph has been kindly provided by NKT Photonics. Fiber alignment and joint loss. A major consideration with all types of fiber connection is the optical loss encountered at the interface. Even when two joints fiber end are smooth and perpendicular to fiber axis and the two fiber axes are perfectly aligned, a small portion of the light may be reflected back into the transmitting fiber, causing an attenuation at the joint. This phenomena is known as a Fractal reflection and is associated with the step change in the refractive index at the joint interface, like glass to glass. The magnitude of this partial reflection of the light transmitted through the interface may be estimated using the classical Fresnel formula for light of the normal incidence and is given by R is equal to n1 minus n divided by n1 plus n square, equation 4.1, where R is the fraction of the light reflected at the single interface and n1 is the refractive index of the fiber core and n is the refractive index of the medium between the two joint fiber, that means for R n equal to 1. However, in order to determine the amount of light reflected at a fiber joint, Fresnel reflection at both fiber interface must be taken into account. The loss in decibel due to Fresnel reflection at a single interface is given by loss for Fresnel equal to minus 10 log 1 minus R, equation 4.2. A potential greater source of loss at a fiber-fiber connection is caused by misalignment of the two joint fiber. Any deviation in the geometrical and optical parameter of the two optical fibers which are joined will affect the optical attenuation or insertion loss through the connection. It is not possible within any particular connection technique to allow for all this variation. Hence, there are inherent connection problems when jointing fiber which, for instance, different core and or cladding diameters, then different numerical aperture and or reflective index differences, different refractive index profiles and fiber folds, core elasticity, core concentricity, etc. Figure 4.2 indicates the three possible types of misalignment which may occur when jointing compatible of optical fiber. A. Longitudinal misalignment, B. Lateral misalignment, and C. Angular misalignment. The losses caused by the above factor together with those of Fractal reflection are usually referred to as intrinsic joint losses. Example of possible misalignment between the coupled compatible optical fiber are illustrated in figure 4.2. It is upon that misalignment may occur in three dimensions: the separation between the fiber, longitudinal misalignment, the offset of perpendicular to fiber core axis, lateral, radial, or axial misalignment, and the angle between the core axis, angular misalignment. Optical loss resulting from these three types of misalignment depending on the fiber type, core, diameter, and the distribution of the optical power between the propagating mode. Fiber splice. A permanent joint formed between two individual optical fibers in the field or factor is known as a fiber splice. A fiber splicing is frequently used for establishing a long-haul optical fiber links where a smaller fiber length need to be joined and there is no requirement for repeated connection and disconnection. Splices may be divided into two broad categories depending on the splicing technique utilized. There are fusion splicing or welding and mechanical splicing. Optical figure 4.3 indicate optical fiber and preparation. The principle of scribe and break cutting is a knife edge initiative, crack propagation, then curve model for fiber to be cleaved and is a tension. A requirement with a fiber end for splicing is that they have smooth and square end face. In general, this end preparation may be achieved using a suitable tool which cleaves the fiber as illustrated in figure 4.3. This process is often referred as scribe and break to score and break, as it involves the scoring of the fiber surface under tension with a cutting tool, like a sapphire, diamond, tungsten carbide blade. Figure 4.4 electric arc fusion splicing. An example of fusion splicing aperture. This particular figure with fixed block, electrodes, movable block, fiber, then fiber alignment groove, then this is a push lever, stop lever, and this is a spring, and this is a micro positioner. Figure B is a schematic illustration of the prefusion method for accurately splicing optical fiber. In this initial setting with electrode and fiber, then second is the arrangement of the smooth surface by prefusion with electrode and fiber with the electric arc, then press together. That what is the position? Then accomplishment of splice. Then figure 4.5 indicate technique for tube splicing of optical fiber. A. Snug tube splice, and B. Loose tube splice utilizing square cross section capillary. This is the glass, or in figure A, glass or ceramic capillary for optical fiber, and this is figure B, optical fiber with a cross section with a square cross section capillary. You can see this cross section. Then figure 4.6 indicate multiple fiber splicing using a silicon chip array. This is a silicon chip, this is the ribbon, this is the trimmed area of ribbon, this is the 12K fiber and strain relief area. Then fiber connector. Demountable fiber connectors are more difficult to achieve than optical fiber splice. This is because they must maintain similar tolerance requirement to splice in order to couple light between the fiber efficiently. But they must accomplish it in a removable fashion. Also, the connector design must allow for repeated connection and disconnection without problem of fiber misalignment, which may lead to degradation in the performance of transmission line at the joint. Hence, to operate satisfactorily, the demountable connector must provide a reproducible, accurate alignment of the optical fiber. Optical fiber connector may be considered in three major areas, which are A. The fiber termination, which protect the locates the fiber end. B, the fiber end alignment, provide optimum optical coupling. And option C, the outer shell, which maintain the connection, and the fiber alignment protect the fiber ends from the environment and provides adequate strength at the point joint. Figure 4.7 indicates the ST require multiple fiber connector using a ceramic capillary ferrules. This is the boot, then this is a plug, ceramic capillary ferrule, then alignment sleeve, locking nut, then threaded coupling housing. In figure 4.8, example media interface plug for a duplex fiber connector. Then figure 4.9 indicate multiple fiber connector. In that, figure A represents fiber ribbon connector using V-groove silicon chip. With that, plug, adapters, slit sleeve, look spring, then ribbon fiber cable, its cover, coil spring, metal block, precision metal rod, and V-groove silicon is indicated. In figure B, single mode 10 fiber connector is used. The 10 fiber ribbon is there. That's why 10 fiber connector. Rectangular guided sleeve is a ferrule and guide with guide pin and fiber. Then fiber coupler. An optical fiber coupler is a device that distributes light from a main fiber into one or more branch fiber. The latter case is more normal, and such devices are known as a multi-port fiber coupler. Requirements are increasing for the use of this device to divide or combine optical signals for application with optical fiber information distribution system, including data buses, LANs, computer network, and telecommunication access network. Optical fiber couplers are often passive devices in which the power transfer takes place either option A through the fiber core cross section by butt jointing the fiber, or by using some form of imaging optical between the fiber like core interaction type, or option B through the fiber surface and normal to its axis by converting the guided core mode to both cladding and refracted mode, which then enable the power sharing mechanism like surface interaction type. Multi-port optical fiber coupler can also be subdivided into the following three main groups. First, 3 and 4 part coupler, which are used for signal splitting, distributions, combining. Star coupler, which are used for distributing a single input signal to multiple output. Waveguide division multiplexing device, which are specialized form of coupler designed to permit a number of different peak wavelength and optical signal to be transmitted in a parallel on a single fiber. Then in this context, wavelength division multi-coupler either combine the different wavelength optical signal into the fiber multiplex, or separate the different wavelength optical signal output from the fiber. This is a demultiplex. This is a class figure 4.2 indicate classification of optical fiber coupler: core interaction type and B surface interaction type. This is the figure 4.11 indicating optical fiber coupler types and function, with A 3-port coupler. 3-port coupler A is there. This one. Then option B is a 4-port coupler, A and B. C is a star coupler. D is a wavelength user multiplexing and demultiplexing coupler. Now we discuss equations that are used to solve the example in this particular practical. So first, assuming uniform excitation for all the optical modes in a multi-mode step-and-trace fiber, the overlapped area between both fiber cores approximately gives the lateral coupling efficiency and dual suffix lateral. Hence, the lateral coupling efficiency for two singular step-and-trace fiber written as n lateral equal to 16 n1 by n squared divided by 1 plus n1 by n raised to 4 1 by pi in bracket 2 cos inverse y by 2a minus y by a in bracket 1 minus y by 2a square root that is 1 raised to 1 by 2. Equation 4.3, where n is the co-refractive index, n is the refractive index of the medium between the fiber, y is the lateral offset of the fiber core axis, and a is the fiber core radius. The lateral misalignment loss in decibel may be determined using a L loss lateral equal to minus 10 log 10 and lateral in dB. This is equation 4.4. Then the lateral misalignment loss in multimode gradient fiber with refractive index gradient that is equal to L is equal to 2 by pi in bracket y by a in bracket alpha plus 2 divided by alpha plus 2 4 0 less than equal to y less than equal to 0.2a. Equation 4.5. The lateral coupling efficiency was given by N lateral is equal to 1 minus LT. The excess loss, which is defined as the ratio of power input to power output given by excess loss for 4-port coupler, that is 10 log 10 P1 divided by P3 plus P4 dB in dB. Equation 4.7. The insertion loss, however, is generally defined as the loss obtained for a particular port-to-port optical path that is given by insertion loss equal to port 1 to 4, that is equal to tan log 10 P1 by P4 into dB, equation 4.8. The crosstalk, which provide a measure of direction isolation achieved by the device, is ratio of the backside power received at the second input port to the input power, which is maybe written as crosstalk in bracket 4 port coupler equal to tan log 10 P2 by P1 into dB, equation 4.9. The splitting or coupling ratio indicates the percentage division of optical power between the output ports. Split ratio is P3 divided by P3 over P4 into 100%, equation 4.10. The splitting loss is related to the number of output port and following. That is given by splitting loss equal to input star coupler equal to tan log 10 dB, equation 4.11. For a single input port and multiple port output port where ij equal to 1 and the access loss is given, then access loss for star couplers is equal to tan log 10 in bracket pi divided by limit of 1 sigma 1 to m pj into dB, equation 4.12. Total access loss equal to m into access loss plus port number of coupler plus splice loss, equation 4.13. Insertion loss equal to splitting loss plus access loss for 4 state in the equation 4.14. And the reflection are dependent on the Bragg wavelength lambda suffix b given by lambda suffix b over 2n, equation 4.15. And where n is the refractive index and the material and the delta is the grating period or grating period. Now we solve the example with the help of Scilab. Question 1. An optical fiber has the core refractive index of 1.5. Two length of the fiber with smooth and perpendicular of the core axis and face are butt together. Assuming the fiber axes are perfectly aligned, calculate the optical loss in decibel at the joint due to Fresnel reflection where there is a small air gap between the fiber and faces. So for this example, we have to use the data as per given equation 1. Data 1. Then use equation 4.1 and 4.1 that is discussed in the earlier. In this particular example, n1 is given 1.5, n is given 1.0 core refractive index, magnitude of the Fresnel reflection at the fiber air interface. So use this equation, r is equal to n1 minus n divided by n1 plus n squared. Optical loss, that is equal to loss free minus tan log 10 1 minus r, and final result display, that is with the help of printf. So printf, that is equal to optical loss file, and print off, that is total loss due to Fresnel reflection at the fiber joint. And finally we have to print the result. So optical loss is 0.8 dB and total loss due to Fresnel reflection at the fiber joint is 0.35 dB. So let's try to run this program with the help of Scilab so we can understand briefly. So Scilab I already opened. So new on Scilab, then save the program. So first n1 is equal to 1.5 core refractive same r is equal to equation 4.1 use 4.1. Then loss equation for optical loss that I already described earlier in the document, and then display the result with the help of printf. So let's execute this program. So with the help of this particular key, execute, and we can see the result. Okay, so optical loss is 0.18 dB and total loss due to Fresnel reflection at the fiber joint is 0.35 dB. We can see the result in the variable browser also, and n1 r and loss free. This is the answer. Now we clear this answer for next example. Question 2. A step index fiber has a core refractive index of 1.5 and core diameter of 50 micrometers. The fiber is joined with a lateral misalignment between the core axis of 5 micrometers. Estimate the insertion loss at the joint due to the lateral misalignment, assuming a uniform distribution of the power between all guided modes when there is a small air gap at the joint. And the option B is the joint is considered index watch. So we use the given data in this particular equation, use the equation 4.3 and 4.4 to solve this particular example. So n1 is equal to 1.5 core refractive index, n is equal to 1.0, y is equal to 5 10 to minus 6 meter, lateral misalignment, a is equal to 25 10 to minus 6 meter, core radius. Then as for the equation 4.3 and 4.4, eta for lateral one is 60 n1 by in raised to 2 divided by 1 plus n1 by n raised to 4 into 1 2 cos inverse y by 2a minus y by a square root of 1 minus y by 2a square. And insertion loss equal to loss suffix lateral equal to minus tan log eta lat. Then coupling efficiency, there is eta suffix lateral for one same equation for this particular value. Then once again we have to calculate the insertion loss, and finally displaying the result. So printf insertion loss, there is a small air gap at the joint, and finally printf insertion loss, the joint is considered index match. What is the loss at the particular time? So kindly we have to check this calculation with the help of Scilab. Okay, so N1 and YA, that is given. Coupling efficiency and coupling insertion loss, we have used equation 4.3 and 4.4, and coupling efficiency once again calculated with the help of equation 4.3 and 4.4, and finally displaying the result. So execute this, save and execute, and we can see the result. Okay, so insertion loss, there is a small air gap at the joint, is a 0.94 dB, and insertion loss, the joint is considered index match, that is 0.59 dB. So you can see the clear difference. You can also see the result in the variable browser once again. So this is the same result we have displayed in the document. Okay, now once again we have cleared this. So for the next example, question 3, a gradient index fiber has a parabolic refractive index profile alpha 2 and a gold diameter of 50 micrometer. Estimate the insertion loss due to a 3 micrometer correctly misalignment at a fiber joint when there is an index matching, and assuming there is a uniform illumination of all guided modes only, and there is a uniform illumination of all guided and leaking mode. So this is the for this example we have to use equation 4.5 and 4.6 that already discussed earlier in this particular document, and this is a given data y is equal to 3 into 10 to the minus 6 meter lateral misalignment, and y is equal to 25 into 10 to the minus 6 meter in the core radius. L suffix t, that is equal to 0.85 into y divided by misalignment loss, and eta suffix L t, that is the coupling efficiency 1 minus LT, then loss minus 10 log 10 eta LT insertion loss, then misalignment loss once again for 0.75, and similar kind of equation eta L2 and loss suffix LT for coupling efficiency and insertion loss. And finally displaying the result, printf insertion loss, there is a uniform illuminating of all guided modes only. Then in printf the insertion loss, there is a uniform illumination of all guided and leaky modes. Okay, so what is the result in this particular case? That can be checked with the help of Scilab. So same code is executed with the help of Scilab. This is the code, this is the given data YA, and then we use equations as we have described earlier, and then we click on the execute. So save first of all and then run. So you can see insertion loss, there is a uniform illumination of all guided modes only 0.47 dB, and insertion loss, there is a uniform illumination of all guided and leaky mode is 0.41 dB. So this is the variable browser, you can check the result for all the value for L suffix T1, L suffix T2, loss and efficiency for both the case. Okay, so finally we got the same result in this particular document. Then question 4 is about a 4-port multi-port fiber FD coupler has a 60 microwatt optical launch into the port 1. The measured optical power at port 2, 3, 4 are 0.004, 26.0 and 26.5 microwatt respectively. Determine the access loss, the insertion loss between the input and output ports, the crosstalk and the split ratio for the device. So for solving this particular example, use equation 4.7, 4.8. So P1, P2, P3, and P4 all are given in terms of watt. So P1 is in watt input power at port 1, P2 is equal to watt in output power at port 2, P3 is equal to some value watt output power at port 3, P4 is value watt output power at port 4. Access loss equal to 10 log 10 P1 divided by P3 plus P4 for calculation of access loss. Insertion loss 10 log 10 P1 by P3 for calculation of insertion loss port 1 to 3. Insertion loss for 2 and log 10 P1 by P4 calculation of insertion loss port 1 to port 4, and crosstalk 10 log 10 P2 by P1 calculation of crosstalk, and split ratio that is given by P3 divided by P3 plus P4 calculation of split ratio. And finally displaying the result with the help of printf. So printf access loss, printf intrinsic loss port 1 to 3, printf intrinsic loss port 1 to 4, printf crosstalk, printf split ratio. So let's try to run this example with the help of Scilab and we check the result. So same code is executed in the Scilab. So P1, P2, P3, P4 all are given, and we have just used the equation that we discussed earlier in this particular document to find access loss, insertion loss, crosstalk, and split ratio. Then execute this code, save and execute, so we can get the result. Okay, so access loss is 0.5 dB, intersync loss is port 1 to 3 is 3.60 dB, intersync loss port 1 to 4 is 3.39 dB, crosstalk is minus 41.8 dB, split ratio is 48.6 dB. So same result are displayed in the particular variable browser. So this is the same result are also written in this particular document. So we have now cleared the variable browser to solve next example. So question 5, a 32 by 32 port multi-mode fiber transmission star coupler has a 1 milliwatt of optical power launched into a single input port. The average measured optical power in each output port is 14 microwatt. So calculate the total loss incurred by the star coupler and the average insertion loss through the device. This is the for solving this particular example. We have used equation 4.8, 4.11, and 4.12 that is discussed earlier in this particular document. So Pi is equal to 1 into 10 raised to minus 3 watt input power at port 1, P output is equal to 40 into 10 raised to minus 6 watt output power at other ports, and is equal to 32 ports. Calculating splitting ratio loss equal to 10 log 10, calculation of access loss equal to 10 log 10 Pi by P out into N, then calculation of total loss equal to addition of splitting loss and access loss, and calculation of average insertion loss, that is equal to Y, insertion loss equal to 10 log 10 Pi by P. And once again displaying the result with the help of printf. So printf total loss is and printf average insertion loss is. Okay, so let's try to run this command in the Scilab to check the result. Same Pi, Po, and N are given. We have to find splitting loss, access loss, total loss, and insertion loss with the help of given equation 4.8, 4.11, and 4.12. It is discussed earlier in this particular document. So execute this code and we can check the result. Okay, so total loss is 18.54 dB and average insertion loss is 18.54 dB. You can also check in the variable browser with the same result, and we can also display the same result in this particular document. Example 6, a number of 3-port single-mode fiber couplers are utilized in the fabrication of 3 ladder coupler with a 16 output port. The 3-port coupler each have an access loss of 0.2 dB with a split ratio of 40%. In addition, there is a splice loss of 0.1 dB at the interconnection of each state. Determine the insertion loss associated with the one optical path through the device. So this is the code. This is the example is given. Use equation 4.1, 4.8, 4.11, 4.12, and 4.14 to solve this particular example. So access loss equal to 0.2 dB access loss of each port. Split ratio is equal to 5, so 100% split ratio. Multiplied by 100% for split ratio, n equal to 60 port, m is equal to 4 for n equal to 60 port. And split ratio loss equal to 0.81, that is a dB splice loss. Now calculation of total access loss equal to m into access loss plus 3 into splice loss, and calculation of splitting loss equal to splitting loss of 10 log 10 and calculation of insertion loss, that is insertion loss of addition of total access loss plus splitting loss. And finally displaying the result in the command window. So insertion loss, printf insertion loss. Okay, so we have just check the result with the help of Scilab. So control V. First we clear the response so it will not disturb the answer. Okay, so and again execute the command. So we can check the result. Insertion loss is 13.14 dB. And for once again I remind you to just first you have to calculate by your own with the help of pen and notebook, and then try to run this command with the help of Scilab. Okay, and I think this is last example maybe. Question 7, an FBG is developed within the fiber core which has a refractive index of 1.46 and find a grating period for it to reflect an optical signal with a wavelength of 1.55 micrometer. So for the given data use equation 4.15 to solve this particular example. So n is given, n equal to 1.46 core refractive index and lambda is equal to 1.55 in micrometer wavelength. So grating period use equation 4.15, lambda is equal to lambda b divided by 2n, and displaying the result the printf grating period is. So let's check the result. Very simple example is this. So yes, we have to first clear and clear the console window behind, execute this command and check the result. Okay, so Dating period is 0.53 micrometers. So let's check the results. Yes, same is displayed in this particular document. So finally, we conclude these experiments about to know what is optical fiber connection, joint, coupler, and isolator. The mechanism which cause optical loss at the fiber joint are outlined with particular attention being paid to fiber alignment. This experiment also demonstrate mathematical equation with example for optical fiber connection, joint, coupler, and isolator. Note, demonstrated examples are given in Optical Fiber Communication Principle and Practice, John M. Senior book, 3rd edition, and example number are 5.1, 5.2, 5.3, 5.7, 5.8, 5.9, and 5.10. Thank you.